Good morning, students. So in the previous class, we have been discussing the onboard communication interface in an embedded system. Onboard communication interface means the different types of communication interfaces that the ICs within an embedded system can use to communicate with each other. That is within the embedded system. Okay. So already we have seen I2C bus. Okay. SPI we have seen. Okay. Then we have also seen the working of UART interface. So today let us study one more onboard communication interface, that is called as one wire interface. Okay. So the one wire, the word one wire in this interface indicates that there is a single wire used for communication between the master and the slave devices. As you can see in the diagram, there is one master device, that is the microcontroller, and there are three slave devices. Okay, and there is a single communication line. Okay, so since there is a single line, okay, so the communication is the data can either flow from the master to the slaves or from slaves to the master. So it allows half duplex communication, and also there is no clock pulse. Okay, so it is an asynchronous communication. So this one wire interface allows asynchronous half duplex communication. Okay, so there is a single wire for data communication between the master and the slave devices. Okay, and also remember that the same wire can be used to power these slave devices. As you can see in the diagram here, the same wire is connected to VCC through a resistor. So these slave devices internally they use a capacitor to draw the power from this power line through the same communication wire. So the same wire can be used for transferring the data as well as for powering up the slave devices. Okay, so this is how the communication, this one wire interface looks like. And for communication, this master or the microcontroller is going to initiate the data transfer. So initially this master will send a reset pulse on this communication line. Okay, so the master is going to send a reset pulse. If there is any one of the slave device which is active, then it will send a presence pulse back to the master. So initially the master will send a reset pulse. If there is any slave that is active, it will send a presence pulse saying that I am ready for communication. Then this master will send a 64-bit unique address of the slave devices. Each slave devices that are connected to this one wire interface will have a unique global 64-bit ID. So that ID will be sent by this master on the communication line. Okay. Then the master will send whether it wants to read or write the data. Then suppose the master wants to write the data to any one of the slaves, it will place the data on the data lines and that will be received by the slave devices. And if the master wants to read some data from the slave device, the slave will place the data on this one wire interface. That data will be received by the master. So this is how the communication takes place in case of your one wire interface. Okay. So let us next study one more type of onboard communication interface, that is called as parallel communication interface. Okay, so the word parallel indicates there will be more than one data lines present. So here you can see, suppose if it is an 8-bit data bus, if the processor, microcontroller or the microprocessor has an 8-bit data bus, this peripheral device should also have 8-bit data bus. So here then I will have D0 to D7. So this will be the parallel bus. Okay, so through this bus the parallel communication takes place. So the data bus, this is the bus through which the parallel data flows between the processor, the host and the peripheral device. Okay, then this read bar and write bar and this chip select bar, these three signals are used to control the data communication. Okay, so initially each device, this peripheral device, will have a range of addresses. Whenever this processor places that range of addresses on the address lines, so that address will be sent to this address decoding circuit. Okay, then this decoding circuit is going to generate one chip select line. Now when this chip select bar is low, active low, so this whenever the particular address of this peripheral is placed on the data lines of this processor, okay, that address will appear here in the address decoder. It is going to generate a low pulse. Then this peripheral device gets activated. Now it is ready for communication. Now, after placing the address on the address lines, the processor will either want to read the data or write the data. So suppose it wants to write the data to this peripheral, then it will activate this write bar line. So it will send a low signal on this. Then the processor or the host controller will send the data to be written on this data lines that will be received by the peripheral device. Now suppose after selecting this peripheral device, okay, the processor wants to read the data, it will enable only this read bar line. So it will enable this read bar line. So when this is enabled, the peripheral device will place the parallel data on these data lines, and that data will be received by the processor. Okay. So this is how the parallel communication interface works. Okay. There will be a data bus for data transfer and some control signals such as read bar, write bar, and chip select bar for controlling the communication. Okay. This is about the parallel communication interface. So till now we have studied the onboard communication interface. Okay, so let us now study which are the different external communication interfaces that can be used in an embedded system. External communication interface means these are the communication methods which can be used by the embedded system to communicate with other embedded systems which are outside the embedded system. Okay, external devices which can communicate with the embedded system. Okay, among these external communication interfaces we have RS-232, Universal Serial Bus, Wi-Fi, Zig Bee, infrared communication, and Bluetooth. Okay, so let us study them one by one. So RS-232C is one type of communication interface which was earlier used for communication between any two communicating devices. So this RS, this R stands for recommended, S stands for standard, recommended standard 232, this C stands for the version. Okay, so this RS-232C was first designed by Electronics Industries Association. Okay, so this RS-232C is a point-to-point communication method. That means suppose the computer wants to communicate with a printer, then there should be one RS-232 cable between the computer and the printer. Similarly, if the computer wants to communicate with any other device, then there should be a RS-232 cable between the computer and that device. So in this way, this RS-232C is a point-to-point communication interface. There should be a cable between any two communicating entities. And this RS-232C, it supports serial data transfer. Okay, so the data transfer will be serial over this RS-232 line. And the maximum length of the cable that can be used between two communicating devices for this RS-232 interface is up to 50 feet maximum. And the maximum data transfer rate is up to 20 kilobits per second. Okay, so these are some of the features of RS-232C interface. This RS-232C interface uses two types of connectors. One is called a DB, one is called as DB9 connector. Okay, as you can see here, there are 9 pins. Okay, so it is called as a DB9 connector. Okay, and the other type of connector that is used in case of this RS-232C is DB25 connector. There will be 25 pins. Okay, so let us understand how this RS-232C communicates with other device.
The unit quantum communicates to machine tools using the RS-232 serial communication protocol. The term serial means data is sent 1 bit at a time. Sending more than 1 bit at a time is called parallel. RS-232 is a specific serial protocol that defines the wiring and flow control used to send these data bits. It was originally designed to send data between computers using modems and a telephone line. And you will see this legacy as we learn more about the protocol. Let's begin by looking at the wiring. We start with 2 pieces of equipment that need to communicate with each other. To keep it simple, let's say one only sends and the other only receives. In reality, both sides send and receive, but if you understand how the communication works in one direction, you can apply it to both. Data is generated by the sender, which puts it in a send buffer that temporarily holds the data. To get the data from the sender's buffer to the buffer on the receiver, we need a wire. On the sender side, this is the transmit data or TX wire. On the receiver's end, this is the receive data or RX wire. Once these are connected together, the data can flow from the sender to the receiver. This is the simplest case. But the designers of the RS-232 specification asked a few basic questions. What if, for example, the receiver is missing? In our simple case, the sender would continue to transmit the data to nowhere. So the RS-232 designers added a control wire, which tells the sender that the receiver is there. On the sender side, this wire is called the Data Terminal Ready, or DTR. On the receiver's end, this is called the Data Set Ready, or DSR. When these are connected and the proper voltage is set by the receiver, the sender knows the receiver is there, and once again, data can safely flow. But what if the sender transmits the data too fast? How fast this data is sent is called the baud rate. If the baud rate is so high that the receiver cannot get the data out of its buffer fast enough, the buffer overflows, and once again, data is lost. To counter this, the designers added another control wire so the sender and receiver can coordinate when to send the data. On the sender side, this is the request to send, or RTS. On the receiver's side, this is the clear to send, or CTS. With this additional line, the receiver tells the sender when it needs to pause, and buffer overruns are avoided. Using this send-stop signal is known as hardware flow control. The RTS-CTS wire is the hardware that controls when data flows between the devices. For completeness sake, there are two more wires defined in the RS-232 spec. Both of these are related to modems, so seldom used anymore. These are the Data Carrier Detect, or DCD, which tells the modem when an analog signal is being received from another modem, and the ring indicator, or RI, that tells the modem that the phone is ringing. Since we're talking about modems, you may be thinking, wait a minute, there are no modems between the Quantum and the machine tool. And you're right. Instead of using modems, you can loop the control wires from the sender side to the receiver side on the same device. And then the device will tell itself that things are ready to go even when there is no modem. Because null is a programmer term for nothing or empty, and there is no modem, this is called a null modem. With a null modem, we're back at the most basic case, and we only need to connect the transmit and receive wires between two devices to transfer data. To be technically accurate, we also need a ground wire to establish where the signal voltages are referenced from. This third wire is called the signal ground, or SG. With these three wires, we can communicate between two RS-232 devices.
So as you can see here, okay, so this RS-232C was mainly designed to communicate through the modem devices. Okay, so through the modem, the earlier devices used to communicate with each other. But nowadays, modems are rarely used here. So in absence of modem, it is called as the null modem connection. So how to connect this RS-232 cable to a computer in case of a null modem when there is no modem? Directly, if I want to communicate bypassing the modem, at that time, the transmit line of this cable, RS-232 cable, should be connected to the receive line of the computer. The receive line of the RS-232 cable should be connected to the transmit line of our computer. Then the ground cable should be connected to the ground of the cable. Remaining this request to send and clear to send, they should be shorted together, and this data set ready, data terminal ready, data carrier detect, all the three lines should be shorted. Okay, so this is how we have to use the RS-232C cable.
Arrangement is descriptively called a three-wire null modem. This is what the Quantum uses. Of course, this means the functions that the
Okay, so till now we have studied the working of one wire interface, okay, Also we have seen how the parallel interface works, and also we have started discussion on the external communication interface, and we have seen how the RS-232 interface works. Okay, so in the next talks we will be studying the remaining external communication interfaces. Thank you.